settings. I don't know. Okay, so it looks like we are recording. I'm going to do my best to stand here and not wander around. So welcome, everyone. It's nice to see everybody here in person and also our folks online. I want to welcome you to our first Maptime Davis in the new Physical Sciences and Engineering Library space. This is our home for the quarter, and I'm super excited that we get to use it because it's just cool to get to use a new space. So I should introduce myself. My name is Michele Tobias. I am a data scientist who specializes in geospatial data at UC Davis DataLab. And I am one of the coordinators of Maptime Davis and also one of the founding members of this group. I think this is a really cool space to be in, like to be able to bring workshops and education to folks. Actually, I had 2 emails this week from former students telling me about their really cool success stories from workshops and opportunities they've had working with me. So it just makes me more excited to do this kind of stuff because the more we share together, the more people can learn and the more cool things they can do in the world and maybe do a little bit more good. So I am glad you are here. I don't promise an earth-shattering, life-changing experience today, but who knows? It can happen. And so my co-presenter today is Alex Mandel. He's over here working on the Zoom stuff while I get us started today. So Maptime Davis, if you're unfamiliar with what we are and what we do, we've been around since I think 2017. Yes, 2017. And we are a part of a larger organization, loosely organized, called Maptime, that happens all over the world. People can start these chapters wherever they want. But ours is here in Davis and sponsored by DataLab at the moment. So we tend to focus a little bit more on research tools versus some of the other Maptime sometimes do a little bit, have their own flavor to what they teach, but this is us. Today, we are going to be working on learning how to work with spatiotemporal asset catalogs to download some satellite data from the NASA satellite STAC catalog. Important things you need to know. Shoot, how are we going to get you guys the materials? So for the folks on the call, I'm going to drop a link in the chat. Sorry, we're still working out how to be hybrid effectively. For folks in the room, let me. I think you can probably search and find this GitHub repository, but let me see if I can make this readable in the room. Unfortunately, nobody has stocked the room. We have this giant whiteboard. There are no markers. So it's the drawback of being in a new room. Let's just split this up so it's a little bit more readable. Okay, so for the folks in the room, our workshop materials are on a GitHub site. So if you go to github.com/Michele Tobias with 1 L, all one word, and then /workshop-stack without a K, then you will find the materials for today's workshop. So we're going to start. There's 2 parts to this. We have a reader with intro materials that's just written, and then we have a Quarto file for R that functions like a notebook that we're going to work through the coding part of this today. So everyone who's in the room, have you found the repo yet? See some thumbs up. I see some confused looks. I'm going to give people another minute to find it. So github.com/Michele Tobias /workshop-stack. This is a lot easier when everyone's on Zoom because I just dropped the link, but I can't do that here for the folks in the room. And I can't write it on the whiteboard because I didn't bring pens with me. So, all right, are we good to go? Anyone still having troubles finding it? Okay, nobody is saying, oh my God, stop. So let's soldier on. Don't need to save that. So if you land on our homepage for this workshop repo, you will find something that looks a little bit like this. Probably your font is not quite this big, but for the folks in the room. Oh, I'm not. I need to share. Okay, this is what I'm talking about when I say we've got a learning curve. Okay. All right. I'm gonna try to make that smaller so that's not in the way. Okay, so now the folks online can see and the folks in the room have Zoom stuff in the way, but we will we'll deal. Okay, so this is our landing page for this. You'll notice we have the link to our reader here, and then we also have the link to the Quarto notebook. We just need the reader for right now to get started, and then we'll go to the Quarto file later. So I clicked on the link for our reader. And this is what we've got. So we already introduced ourselves. So you were doing yeah, I've totally forgotten who was doing what for the plan. You were going to introduce the STAC stuff, right? And then I was going to do with the API stuff. Okay. So Alex is going to take over. Why don't you introduce yourself too? I didn't introduce you very well, and then I will.
On screen? Yeah. Cool.
Yes.
Hey everybody, I'm Alex. I'm a geospatial engineer at a company called Development Seed. We're a consulting company with doing stuff with data, a lot of satellite data. I'm also an alumni and a founding member of MapTime. Just give you a background on this. So today we're talking about something called Spatiotemporal Asset Catalog. It's a big mouthful. That's why everybody just calls it STAC, S-T-A-C. So if you're searching around online, that's the way to search for it. STAC is a community developed, soon to be standard. I think it's in progress. I can't remember. But there's a community standard and we're trying to get it certified by a standards body. Basically, it's a consistent way of cataloging data for Earth sciences, basically. And so it was originally started for satellite data, but it can be applied to all sorts of other geospatial data. And the reason why it came out was because everybody was making their own catalogs and their own way of cataloging. And so every single data provider you went to, via NASA or USGS or European Space Agency or Maxar or Planet, they all had a different way of bringing their data up, and there was no consistent way for you to access that data the same across all of those. And so there's a bunch of people from all these different organizations were like, hey, let's make it consistent.
Turn off your speaker on your laptop and I'll stop that.
Good, man. So that's the background behind STAC. For those online, there's a fun echo in the room. We're good. Great. Yeah, so, and the reason why this gets really important is when you have lots and lots of data, like hundreds of millions of files, you need a way to use a computer to search through all of that and find your stuff. You don't want to be going one by one, clicking through a search interface on a website to get every single file you need for what you're trying to do. You want a way to write code or make something repeatable. And if you have to work with thousands of files at the same time or like one after another, you want to be able to queue that up, right? So we needed a sort of a language for looking over all of those records easily. And that's what STAC is.
Anybody that's ever tried, I think anybody that's ever tried to manage more than like 5 satellite images on their computer probably has an idea of what that's like and why you need this kind of catalog, because it's really easy when you look at all these weird file names, like what is this? Where did it come from? You need all that metadata, and that's what this is helping you do, is keep all of that straight. So
Any questions? Today, we're specifically going to look at how to access these STAC catalogs using the R programming language. But as you'll see, you can use any programming language you want. And there's lots of graphical tools too, like ArcGIS and QGIS both have STAC plugins, so you can search STAC catalogs from those also. Let's see. So the important points: filter based on metadata. So like where an image was taken, when it was taken, how much cloud cover was in the image, if that's available, or other parameters that data collectors have about their images, which band you want. There's all sorts of different ways that you can filter the data. This really helps with reproducibility, because if you can write it down as a query in code, you can give that to someone else and they can get the exact same data set that you wanted. And then the next part of this that we're going to talk about, which is sort of an add-on, is if the data that's in the STAC catalog is in what we call a cloud optimized format, which I'll get to in a sec, you then don't have to download all of it. You can download little parts of it that are just the parts that you're interested in. All right, so the foundation of STAC is that when you interact with the STAC catalog, everything is in a file format called JSON. If you're not familiar with JSON, it's a text file. You can read it with any text editor, but it's structured text so that a computer can easily walk through a nested tree of values. And we'll probably need to look at an example of that for that to make a lot of sense to people.
What it looks like to me.
It's definitely like a table of contents. Yes, yes. Okay, so the question for those online was, sorry, yeah, how is JSON related to GeoJSON? The answer is JSON is a format for describing any data. GeoJSON is specifically for describing geographic data. Specifically, GeoJSON is for points, lines, polygons, so geometries. And you are correct that STAC is actually valid GeoJSON. So if you do a STAC query, you actually get back a GeoJSON object that you can load as a layer in any of your GIS applications. And so we'll get to that, the foundation of that, which I think will make a little bit of sense here. The basic organization, and I did this from the bottom up, is at the lowest level, you have an asset. An asset is the actual file. And so you can have lots of files for one particular thing that go together. And so you can have several assets. And when you group those assets together, it's an item. And the item has a bunch of properties, which is what makes it a row in a GeoJSON. It has a geometry. It has a bounding box. It usually has a time range for when it's valid. So like, if it's geographic data, when is the time period that that geographic data describes? And then anything else about like what satellite collected it or what other tool was used to collect it, who made it, when they made it, any of those properties that would be shared across different samples that you take. So like when you think of a satellite takes many pictures over time. Each of those pictures that a satellite takes is one asset. Sorry, yes, is one asset. If that picture is actually different bands, so like a red, green, and a blue band, and they're stored separately, each one of those is a different asset, and combined, they make an item. And then each picture that you take is a different item. And when you group all the items together, you have a collection. So if we're going to go with like an example we're talking about kind of today, you have Landsat 8. And Landsat 8 has 12 bands, I think. Something like that. And so each scene in Landsat is one item. each band is an asset within that item. And then usually there's like a preview and a metadata file and some other extra files about that. And those are all assets. And then Landsat 8 is the collection. So if you wanted to search for Landsat 8 data, you would search the Landsat 8 collection and then do a filter over space and time and bands and other stuff to get the items you want. And then once you have the items you want, you can ask it for the specific assets or files that you want from that. And that's what the workshop today is going to show you how to do. And then going above that, a catalog is basically multiple collections. So Landsat 7 is a collection, Landsat 8's a collection, Sentinel-1's a collection, Sentinel-2 is a collection. These are all different satellites, different satellite products. And then the key to making this all work is it's not enough to make the catalog, but you have to put it online in a way that people can interact with it. And that requires something called an API, which we'll get to in a minute. Okay, so then the other part I said I was going to talk about today was cloud optimized formats. Today specifically, I'm just going to talk about one. It's called cloud optimized GeoTIFF. This is a format for raster data, so pixels, rows and columns of pixels. It's like taking a picture. And the cloud optimized GeoTIFF, who here's used the GeoTIFF before? Anyway, it ends in .tiff. You load it in Arc or QGIS. Yeah. There are other formats like NV has its own format, and what are the other common raster formats these days? There are a lot. This particular type is they've taken the general GeoTIFF, which people have been using for 30 years, and reorganized it internally by geography so that you have the file in pieces internally, and they're by like a bounding box. So it's like you take the whole picture and you grid it into chunks, and then each of those chunks can be read separately. And so the idea here is if you had a big, huge image, but you only wanted to read one little corner of it, you don't have to read the whole file now. You can just read the one corner. Because there's a little index at the beginning of the file that lets your client, so whatever software you're using, ask for what is the spatial extent for each of those little chunks and find the matching one and then just read that little one. So instead of downloading a 10 gig file, you could read 1 gig of the file. Yeah, so the question was that this is a grid over the pixels, and the answer is yes. It's basically internal to the file. You're dividing the file into pieces that contain parts of the columns and rows that are next to each other. If you want to read more about this, some colleagues of mine and I wrote a whole guide to this on cloud optimized geospatial formats. There's pictures, there's code, there's explanations about all that stuff.
I think, one thing to know, I just want to clarify, well, two things, I guess. So the JSON that we were talking about, the JSON files are the things that describe the items in the catalog. So that JSON data is metadata. It describes the items. The actual items themselves are saved in most cases right now in this cloud optimized GeoTIFF format. So the data you're actually downloading is a GeoTIFF, but it's described in the JSON file. So we've been throwing around file types. I just want to make sure that that's clear. And the other thing is with the GeoTIFFs, you just save a GeoTIFF. Like if you're making one, you don't need to worry about all of the internal stuff. It can be helpful to kind of know conceptually like why it's special and why it's important. But in terms of how we operationally interact with them, you don't need to necessarily worry about, how it's happening, because things like GDAL will just do it for you when you save something as a GeoTIFF, and a cloud optimized GeoTIFF as well. So don't worry too much about in terms of using this that you need to know all of those details or you have to figure out how to do this. You don't. You could if you want, but you don't have to. So Now that we've clarified those 2 points, we are going to talk about, okay, so we have this data, it's sitting on a server somewhere, it's described in this JSON file that becomes our catalog information. How do we actually work with this though? So we've got the pieces, but now we need to know, how do we make this function? The way that we do that through a lot of STAC catalogs, especially when they're online, is through something called an API. So an application programming interface. I never remember what that stands for. Always have to write it down before we give these kinds of workshops. So an API is what you'll hear people say more often than not. And basically an API it's kind of like a programming language, but it's not usually as complex as like R or Python or something like that. Essentially, it is a way of forming a URL, so like a web address, that has some information embedded inside of it that a server can read. So we make this URL, we send it out on the internet, it finds the server says, okay, I know what to do with this. They want to see this piece of information, and then it sends it back and our computer can read it. That might sound super fancy, but I want you to understand that you already do this. Has anyone used an API before? Some of you, okay. All of your hands should be up because if you have done a Google search, you have done an API and you do not realize it. So typically these take the form of what we call a base URL. And then afterwards, after that base URL, there is some information we're passing to the server. So you can think of that as like parameters if you're familiar with like coding in R or Python. But if I go to Google and I search for information on STAC catalog, you can all do this, right? I'm just going to erase this stuff at the end because this is all stuff that is irrelevant to the actual API. And this is our URL. I will switch back to this because it's a little bit more readable. But basically, I'm building a web address, a URL. I've got google.com/search $Q equals, and then STAC plus catalog because I put STAC catalog in the search. That's an API. That's using an API. That's a URL that we're sending to Google to get information back. So our base URL is google.com. No surprise there. The endpoint that we're going to be looking for, so you can kind of think of that as, I like to think of an endpoint as a particular database that I'm connecting to. So our endpoint is the search endpoint. Chances are with Google, I don't know, there maybe have other endpoints that we're not familiar with internally, but that's the one you are going to be working with most often when you're going to Google. The question mark in this URL indicates to the thing that's handling our question. It's saying, okay, this is where the start of the parameters are. So, and then the parameters that we're sending is we're asking it for a query. So in this case, we tell it Q for query equals, and then we give it the terms we want to search for. This is a really straightforward API, and you actually build this query when you search in the box. It basically says, oh, okay, base URL, query terms, put it together, it builds it, and then it sends it. That's what the website is actually doing under the hood. So you all have done this before. You just didn't think you could type this, you know, I don't want to go and load the page. I could actually just build my own Google query URL and send it without having to actually go to google.com first. So hopefully that demystifies what an API is. When we do this with a STAC catalog, it's going to look pretty similar. We're going to have a base URL. So instead of google.com, we're going to have like NASA's Earth data login URL. And then we're going to have some parameters after that that tells the server that we're hitting, what do we want to know? In this case, we're not asking it to give us website information. We're going to ask it to give us information about like what images they have, what collections do they have, but same structure, base URL followed by parameters. So I really don't want to be super complicated. In the reader, we have some more examples of using the Microsoft Planetary Computers API. So if you want to get, you know, another example, check that out. But in terms of time, we're going to skip that today. But definitely a lot more information about how that works. So I think we're good to switch over to the Quarto file. The rest of that is all repeated in the Quarto file in terms of concepts. Okay, so questions at this point. We've been through a bunch of concepts. Alex and I have talked at you quite a bit. Before we switch over to doing some coding and looking at some R code, I want to see if people have questions. And you can check the chat and just make sure. Okay. If you think of any questions, I want you to interrupt. Especially as we start seeing this in action, it might spark some questions. So if we're back on the homepage for our repository here, our GitHub repo, and we click on the Quarto notebook link in the workshop materials, it will open up this file, which is not super exciting to work with on the internet. So you have two options. For those of you who are GitHub savvy, you can fork this repo and download everything onto your computer if you'd like. If you don't want to do that, there is now a convenient download button here on GitHub. So you can just download this particular file and put it on your computer somewhere to work with. So we are going to be working with this particular Quarto file, and we're going to use it in RStudio. So I'm going to get rid of all this extra junk in the way. So what I have done is I've opened up RStudio and I have loaded this workshop_notebook.qmd file. So I'm going to give folks a minute to go ahead and open up their RStudio and load up their Quarto file. What this is, essentially, it's a notebook. It's got text-based information in it, and then there's also code blocks that we can run. So it's kind of easier to read and nicer to look at for just eyes versus trying to read all of the code comments that I started with in this file. And I was like, oh, this is so hard to read. So I switched over to Quarto because I think it's easier to convey information. So for folks online, if you can give me a thumbs up when you are ready to go, when you've opened up your Quarto file in RStudio. And for folks in the room, if you can give me some indication that you are ready, that would be helpful. Thank you. I'm seeing one thumbs up. Yeah, I'm laughing because Naomi, for folks online, Naomi is computerless today, so she's good to go. It's totally okay to just absorb information too. You do not have to follow along if you don't want. Sometimes, especially on a Friday morning, maybe it's just easier to listen, and that's totally fine. That's the beauty of map time. There's no test. If you don't learn anything today and you just want to hang out, that's cool. Half of the point of this is community. Also, I want to acknowledge that folks in the room are probably on EduRoam, which is notoriously slow. So if people are still downloading stuff, that's reasonable. So folks in the room, are we ready to roll? Question? Naomi is pointing out I have 5 messages in the chat window. Okay, yeah, thanks. Sorry, folks on Zoom, you probably can't see that when I'm opening because it hides the Zoom windows, but people in the room can see my Zoom stuff on the screens. Yeah. Okay, so it sounds like we're good to go. Does anyone have questions about RStudio that I can answer at the moment? Probably don't have time to deal with too big of questions about it, but okay, so we have this Quarto file, and it is essentially, it works like a notebook. We've got information in here. I don't know why it's been doing this. When I try to use my laptop touchpad, it starts highlighting the Quarto file. It doesn't do it when I have an outboard mouse. So if yours is not highlighting blue, great. I will just keep unhighlighting things as we go. I don't know why it's behaving that way. It was doing it the other day too. Okay, so in terms of things that can go wrong, that's pretty minor. So the study site that we're going to be working with today. So the point of this Quarto file is to give you some examples, some hands-on experience with working with an API for a STAC catalog, and we're going to do a little bit of exploratory analysis once we download some data. The data we're going to be working with today is data from a place called 10 Mile Dunes, which is in Northern California. It is a very large dune field, so it is visible in satellite imagery. It's a super cool place if you've never been there and are looking for a close by vacation spot. Highly recommend it. It's really quite an impressive place. And there's some reasons we're going to be working with this data. One of them is that it really is a nice area for an example of all the things that can go wrong with satellite imagery, because we have cloud cover. We are on the coast in Northern California. Cloud cover is a big deal, so we need to be able to filter out clouds. The other thing is that this is it's on the coast. It's essentially a beach. So half the image is land, half the image is ocean. The ocean is going to provide a lot of backscatter and a lot of wackiness in our imagery. So we will get to experience that and see it firsthand. So we'll get an idea of what to do about that kind of situation should we have a study site that includes a lot of water, for example. The site actually has a really nice mix of natural areas and some built up areas as well, so we can see what that's going to look like. And it's a really good place to look at a bunch of different things in a satellite image. Probably the most important reason why I picked this is because I actually am a coastal beach plant person. That's what I studied for my dissertation. So of course I'm going to pick dunes. I also, this workshop actually came out of, I went to the Phosphor-G conference, the Phosphor-G North America conference in October, and saw a really cool talk by someone who works at one of the inland dune systems that is owned by the National Park Service. And he did a presentation on working with satellite data to identify the extent of the dune field that he works at. And he did that just basically with using normalized difference water index. And I was like, wait, hold on, like what? So I was like, I want to try that, and started trying to pull down imagery and do the same, like basically replicate his analysis with this dune field in California. I ran into a lot of trouble. And so that's where this workshop was born, because it was like, oh shoot, if I'm having trouble, other people need more help. So that's what why we're doing this workshop, is because I discovered a lot of things and I thought you all would probably be interested to know them and save you some time sorting it all out. Okay, so I think we're going to switch over to Alex to talk about authentication, and then we will, after that, download some images. So switch. Oh, yeah. Let me just, I have it in a file that's easy to get to. I'm just going to change my password afterwards. So if you have like maybe 3 hours to steal my password and do a bunch of stuff on my Earth Data account before I change it. So just be quick if you're going to.
All right, so the first thing we're going to need to do is get all of our stuff set up for this analysis. So there's a little bit of work to do signing up for an account to download NASA data. And then there's a little bit of work to do getting your RStudio set up with all the packages you're going to need. Let's start with the packages, since that might take a little bit of time. So if you go to this install and load library section, if you don't have all of these packages installed yet, go ahead and install them. And if you're using the Quarto notebook, you could just hit the run, which is the little green arrow, or you can copy and paste the code into your R console. If you want to do it. If you got questions about this, let us know. The packages we're going to be using today. So RStack. RStack is basically a library for interacting with stat catalogs in R. Terra is the de facto library for working with raster data in R. R Color Brewer, that's a fun library for helping you pick color ramps for mapping purposes. GetPass is just a little tool to hide your password from the screen when you're putting it in. And then Earth Data Login, that's how we're actually going to authenticate to the NASA server so that we're allowed to actually download data. Anybody got questions about packages? Everybody got that code block running so that those things are installing? Yeah, we discovered in doing this that Earth Data Login requires 4.1. That's the reason, but you can work on the update in the background. So that's the reason I want to start with that first. Okay, the next thing that everybody's going to need to do is in this configure your environment and set up authentication. You need a NASA Earth Data account. It's a free account. You can sign up really quickly. Everybody should follow the link here and go sign up for an account if you don't already have one. You don't need an account to search for data, but because they want to track how much data people download, they require you to have an account in order to access data. I'll give everybody a few minutes to go through and sign up for that. And take questions while we wait. If anybody's got questions.
There's a question online. Yes, you can open the chat and read it. Otherwise, I have to yell.
The Planet API, I haven't. Yeah. So the question is the Planet API stack based? Planet invented their API before Stack, and I believe they have a goal of at some point converting it over so that it is stack based. They do use Stack internally at Planet, and they do contribute heavily to the Stack standard. But I haven't looked at the Planet API very recently, so I don't know how much of Stack is implemented into it.
Yeah. So folks in the room, if you need to plug in and you're near one of these black things on the floor, the black circles, you can plug into those. So if you need to, feel free to do that. Otherwise, there's some plugs around the room. We will work on getting some power strips in here. You know, my laptop battery does not last very long.
Quick check, everybody have a NASA account?
Everyone's still working on it. Okay. Nobody said they were still working on it.
Okay.
We can give you another minute or so. But you gotta let us know.
And the other question is, how are your package installs going? Aside from the person who has to upgrade R.
Sorry about that. We discovered that. I had one of my students run through the workshop and we discovered that. I was glad to find that out because it otherwise would be very confusing today to have a bunch of people not have the right version. But
I can show you later. There is a workaround for an older version that's in our code that's not in the markdown.
yeah, the good news is the materials are going to stay online forever. I don't take down workshop materials. So if you need to catch up, and also because it's a Coro file, you can easily just run code blocks. So maybe keep one ear on the workshop while you upgrade and you won't lose too much.
Okay, so now that we've got our R set up and we have our Earth data account, we're going to go ahead and load the libraries so that they're ready to use. Am I supposed to run the code?
Yeah, run it, because otherwise
Oh, right.
they won't see the pretty output. And then they shouldn't be done.
So hopefully you don't get any error messages when you run the load of the libraries.
When you want help, let us know and we'll think it should go smoothly, but you never know.
Okay. Everybody good for the next step? Looking for some nods.
Remember, if you don't say hold on, slow down, like we can't know. It's really hard to tell when you have like the oh no face from a distance. So just speak up and say, hold on, I need another minute. You know, that's totally fine.
Yeah. The next step is somewhat obscure, and you would probably never know about this if someone wasn't telling you to do this. When you're working with cloud optimized data, there's some settings that you can tell the underlying library that reads the data to do it better and faster because it knows it's on the internet. So like normally, if you think about how you load data, you're usually loading data that you've already downloaded that's already on your computer. When you're working with data that is coming directly from a web server, there's a bunch of tricks to make it go better, especially for these cloud optimized formats. And so that's all you really need to know about this. You can read into it. You can ask me questions later. But basically, if you run this next code block, GDAL, the library we use for reading rasters in most software, does some smarter things that'll make it go way faster. And you're not going to get any feedback on this because it's just setting some things in the background for you. All right, so then the next step is that we're going to get a session with NASA Earth data, which is where we know we're going to get data from. And so the way we're going to do that is we're going to have the code prompt us for our username and password, and we'll type those in. And then we're going to pass that to a special library called Earth Data Login that goes and asks for a valid session. So this is the same thing as going to a website and logging into it. We're basically doing that, but doing it with code.
I'll also note that this is a good thing to do for your code if you're going to be putting it on GitHub and making it public, to prompt yourself for the username and password versus hard coding it. Because if you hard code it and then you put it on GitHub, you just gave it to everyone who can find it. So don't do that. Like sometimes I'll read stuff in from a local file, or I'll just prompt myself for the password in the code. So that way, when I put stuff up on GitHub for other people to see, that I'm not exposing all of my account information. So you don't necessarily have to do it this way, but it's definitely a good idea to not hard code your username and password into code that you might be sharing with other people. Just a heads up.
There are all sorts of other ways to like put these secrets in a file that's only on your computer that you keep out of your code. And you can all ask me about that later. It can get very complicated. This is also a more straightforward way to do it. All right. These in the notepad?
Yeah. Yeah, don't steal my password. There's no way to figure out how to do this that we could think of stuff that didn't work this way.
Oh.
Why did you pick 1, 2, 3, 4?
I know, right? My password is I love cats.
All right, so I put those in. That doesn't do anything until this next step where we actually asked it to sign into the NASA Earth data system. didn't give us an error, so as far as I know, it worked. And this is really interesting because all of this just sort of happens in the background of your R session. And once you've set this up, any requests you make, it automatically knows how to pass the authentication and make sure that you have access. So you don't have to worry about it at all from this point on. Oh, you fixed this earlier. Oh, but you didn't download it.
It's right on there. Typo fix that didn't make it onto this version.
All right, so today the data that we're going to work with is something called Harmonized Landsat Sentinel. Anybody heard about this before? No?
Yeah.
How many people have heard of Landsat before? How many people have heard of Sentinel? Okay, so quick review. Landsat is a program that the USGS and NASA have been running since the 70s. We're on Landsat 9 is the current satellite. And it's a really important satellite because it's been running for that long, and the data across all of those satellites is mostly backwards compatible, meaning you can do a very deep time series analysis over decades with equivalent data. And so a lot of code has been written out there, a lot of algorithms, a lot of papers have been published that show you how to do things specifically using Landsat data. The biggest downside of Landsat is it only takes an image of every place on Earth every 8 days. And so it's not very frequent. And so some people came up with a trick, which is Sentinel. It's a ESA satellite. It's been going for almost a decade now. It has a much higher revisit time. Sentinel-2, which is the satellite we're talking about, has similar bands to Landsat, and it comes every 5 days. There's a little bit of a difference, though. Landsat is traditionally 30-meter pixels, and Sentinel is 10-meter pixels, depending on the bands, because some bands are not as high resolution as that. And so what some scientists have done is they use Sentinel data to fill in a time series of Landsat. So they basically make the two data sets compatible with each other and make it all compatible with Landsat imagery for the entire history of the programs. And now you get 2 to 3 day revisit of Landsat 30-meter pixels. So this is like a fancy way of saying we took 2 different satellites and combined them to make a better satellite.
I'm totally distracted looking at the script. Yeah, like a cricket like this big.
Yep.
All
right.
Consider him good luck.
Anybody have questions about the harmonized Landsat Sentinel? Everybody kind of gets like why this is really nice, right? Because especially on coastal, if we want a day that doesn't have clouds, we got to look often. And so like this is a classic problem in agricultural and tropical regions, coastal areas. Like you can think of all sorts of scenarios where the exact time of year when you want to be looking for some data, you just have clouds. And so if you can get pictures more often, then you have a better chance of finding data that you can actually use, unless you're studying clouds, in which case you're like, I know exactly where to go, which some people do, right? Okay, so this particular data set is in the NASA Earth Data Catalog. We could go to this website and we could look at the graphical search if we wanted to. I already did that just to figure out the information that we need in order to make our own STAC queries to search for this data. And so the important things we need to learn from that are, 1, what is the endpoint for the STAC catalog? And 2, what is the collection that we actually need to search? So the exact name, because when you ask the computer, give me this collection, you have to spell it exactly right or you don't get it. And so by going to the Earth Data Search website, I was able to find that the collection name is this HLS S30V 2.0. And there's a whole product page. You can go read about this. It's linked in here. I think it's the first link, actually, where the USGS talks about what this product is, what's in the product, and tells you this collection name. And then by searching for that in the NASA Earth Data Search, I found out a couple of important pieces of information. The first one is, where is this data stored? And this data is stored in, so NASA has these things called DACs, Data Archive and Access Center, I think. And there's one in particular called LPDAC, which basically has Landsat in it and a few other data sets. And LPDAC is a collaboration between USGS and NASA. Their place where they keep HLS is this server called LP Cloud. And that's important because that is how you find their particular STAC endpoint. There's a whole system to figuring these things out. I just wanted to get you to, like, if you went and looked at all these websites, you'd start to see how I found it. It's not straightforward yet to find where the STAC endpoint is for a particular data set. But if you ask the community, people will help you find it. And if you start to figure it out, you'll see there's a pattern to it, especially with NASA. Any questions about this? Who's ready to try a STAC query? I see one. Okay, yeah, there we go. There were a couple. Okay, so using the RStack library, we're going to set up a connection to this STAC endpoint. So that's what this line here is. And so we needed that URL, which if we went to the URL in a browser, you could see it would return JSON, and you could read through the JSON. So everybody's connected to the STAC server. It doesn't really do anything unless the server's down.
You put stuff in your console so you can see it runs the code in the console. So if it doesn't have an error, then you're good to go.
Yeah. Oh, Charlie had a question about, does the authentication persist across RStudio sessions? It can. Well, okay, so yes and no. The username and password can get stored in a secret file. And if you store it in that secret file, you don't have to type it in every time, but you still have to run the authentication request every time because your session may have expired. We're not using tokens.
Oh.
We're using username and password.
I know, but you still need a token.
No.
Okay. All right.
I think one thing we're discussing here on the side is how long your session is good for. And I actually think the username and password sessions are good for 24 hours usually. But they did introduce a new thing recently where your password may expire every 2 months and you might have to go change your password. So if you get an error that says like invalid or something, go check your account with that URL that you signed up at and make sure that your password's still valid. All right, so the next thing we're going to do is we're going to set up our query. We didn't show you how to do it here, but we basically went to something like Google Maps and zoomed around, or Google Earth maybe we even used. I don't remember exactly which website we used. And we got the bounding box for the place that we wanted to do our research, right? So where do we want to search for our data? And so that's just a rectangle that defines the place on the Earth that we want to search for stuff. And we copied that in, and it's a very specific order of formatting: longitude, latitude, the minimums, then the maximums. Yeah.
Places is that required for the, and does it have to be any, can it be any state box and can you know, decimal place?
Well, it has to be a rectangle. I highly recommend you don't cross the anti-meridian, sometimes called the date line, because not all servers support that. It can be whatever size you want. The more precise you are, the more decimal places you have, the less data you'll have to download. I rounded it for niceties. So it's really a precision thing. Like 8 decimal places roughly will get you into like the meter precision. But if you don't care about that, it's not a big deal. Okay, so we're going to define that bounding box. And the first one, B box, is the format we're going to need for the STAC query. And then we're doing something in preparation for later, which is we're also making a Terra extent object so that Terra is familiar with the same bounding box. It wants things in a slightly different order.
Being the package that handles.
Good. All right, so we're gonna run this, and we plotted it just so that you could be sure you got a box in the right place, and so you can see like the coordinates marked on the axes, give you an idea of like, good, it's in the right place. And this is just geographic coordinates.
I just like to see stuff as a person who is very visual, so it's not exciting, but it's a good check.
If I was doing this for like a paper or something, I would get another library so that I could put a map behind this so you could see the box over a map. It would help you confirm that, in fact, where you're doing the work. It's the same as GPS. So this is WGS84. For stack bounding boxes, it is the same as GeoJSON, which is lat long WGS84, also known as EPSG 4326. Yeah. That's just because all bounding boxes in STAC are encoded that way. And you can optionally do projected bounding boxes. But the main STAC API specification is for WGS84. Okay, so now that we've got our STAC server, which we saved as NASA STAC, we know our collection name. We'll put that in. We know our bounding box. Now we just need to add a date time range. And you do have to do it in this format. You don't necessarily have to have a closing date, but if you don't have a closing date, then it only searches for the one day you put in. So it's preferable to bound your query with an actual opening and closing. And then sometimes a query will return a lot of data. And depending on the server, it may not return it all at once. It may return in something called pages, which is like, hey, here's 100. If you want the next 100, ask for it later. And so we just limited it to 100 so that we don't have to deal with, if there was a ton of responses, having to sort through like, what do we actually want, and checking all the pages. No, in this particular query, we didn't get 100 responses because our bounding box is very small and our date range is very short. But if you had searched like a whole year or 10 years, you could get a lot of data, like hundreds of thousands of records. All right, so we're gonna, this box here is actually just setting up the query. And then in the next box, we're actually gonna run the query. And so this post request is from the RStack library. And we're gonna pass in the parameters we just specified as this search HLS. And then it's gonna hit the server, the API, passing in our parameters and return the results to us. Okay, so if we look at our results, we got 12 matches. It's showing us the item IDs for those 12 matches. So these are HLS scenes. It is telling us that each of these scenes contains assets. And then there are additional metadata properties on these. Yeah.
What if you scroll up a little bit, what sort of, no, the other way, what sort of item is results underscore HR? Is that the GeoJSON or is that an R object? That's,
So the server is going to return GeoJSON. The RStack library, which we use to make the request, is going to format it into a stack collection object. So that's an R specific thing. But if we asked it for just the raw request back, it would have been a GeoJSON. And so if you want that, you can ask for that and then save it and use it however you want. You can actually load it up in a map and see where all the bounding boxes of all the items are and visually peruse through all of your data. Or I should say visually peruse through all the metadata. Because we don't actually retrieve any data with this request. We just retrieve metadata. So information about the files.
Good, because if we return 300 Landsat scenes, we don't want to download that right now. We
Yes.
probably don't want those.
Especially when each one is several gigabytes, right? Okay, so the next thing is we can explore these items. And so if you know GeoJSON, there's a thing called features, right? So there's a feature collection, and then there are features within that. Each feature corresponds to an item in the stat catalog. So you'll get a bounding box and a date time, and it tells you what assets and what items it has in its metadata properties for that one item. We just picked the first one, but we could change that number to any of the 12.
I think the first item actually, because it's actually a good image. So it wasn't just like, oh, being lazy, like that was actually a good one to work with.
I mean, at this point, like, we don't know that. And so, like, I just wanted to check, like, what's in this and get an idea, because you can explore this tree of metadata however you want.
I did actually pull down some.
Yeah.
By the time you get the workshop, it's like clean and pretty, but yeah, we did look at them. And you can certainly download some other ones and see what they look like. They're not that big because we have a pretty small bounding box.
So then looking at this one item, you can see that the item fields, there's a bunch of different things, right? So the geometry, there's bounding box. So geometry is a polygon. And so if this data was not shaped exactly like a rectangle, aligned perfectly with the WH84 coordinate system, you could actually have the real geometry of it. And so this allows for things like you could catalog all sorts of things that are twisted in different ways. And so if you wanted to see the real outline of the data, you can ask for that. And then there's other things. The important one we're going to look at here right now is the properties, because the properties is going to tell us some other important information. And so we just asked the R object to show us what's in the properties, and you can see what the first thing is there, right? Cloud cover. And so this is telling us that this particular collection, every item is going to have a cloud cover property, and that'll have a value, and it'll tell me, in this case, if you go read the documentation, it's like what % of the scene is covered by clouds. In this case, 1% of the scene is covered by clouds. So that means it's cloud free, basically. We can be pretty much guaranteed that almost the whole thing does not have a pixel covered by clouds. And we're just showing that you can walk that tree of information to get down. And the importance of that is because anything you can walk to in this metadata structure means you can filter based on it. And so that's the next thing we're going to do is we're going to set up a filter over the items asking for cloud cover that's less than 10%. And you can pick whatever number makes sense for your study. Sometimes you have to keep increasing that. Basically, there's always this game of, can I get enough data that's good quality? Or in order to get enough data, do I have to, increase that. Like sometimes you'll do 10% and you won't get anything. So you go to 20%. Do I get anything? And then if you get multiple files, there's always the possibility you could combine them to eliminate the cloud pixels, like make a merge of multiple dates. It's less than ideal if you're trying to do something time-based, but sometimes that's how you do it. So we're going to run this filter, and we're just going to save it back to our collection object. And so you can see that instead of 12 items now in the original, if we filter it, there are 4 items that had cloud cover less than 10. So now we've already cut out, we don't even have to look at 8 of the files because we know they're not good enough. Yeah, so on this particular data set, the only things they have are cloud cover and date time. If you look at this item fields, these STAC extensions are optional add-ons, and there might be a bunch of stuff in there that might be useful. And some examples are if you're working with radar data, SAR data, there'll be a bunch of parameters about the actual satellite that was used to collect it. Projection extension can be really useful if the data is in a projection that is not WS84. All of that information will be stored in there, so you'll know what the native projection of the data is. We could go look at the list of STAC extensions. There's a website that lists all of the possible STAC extensions people are using. Citation information can be in there. I mean, basically, if you think someone might need it to help them filter the data, then the person providing the catalog might add it. All right, so now that we've got it filtered down to 4 items, the next thing we want to look at is what are the actual assets in each of these items. And so you can see that the asset section actually has 20 different bands. Well, they're not all bands, 20 different files listed. All the ones that start with B are bands. Fmask is going to be a thing for helping you mask out bad data. You have to go read the documentation to understand in HLS what is in that Fmask. Metadata is going to be a metadata file. I don't actually remember what all of the other things on there are. I think browse is a thumbnail. So you can see, like, for this one time and place, we actually have 20 files. But we don't need to work with all of those all the time. We just need certain ones. And so we wanted to look at the list of those so that we could decide which ones that we want to use for the next part.
Okay, so just to recap where we're at, we've made our query for our STAC catalog. We've sent that query and it has returned information back about what data sets the catalog has that meet our specifications. So, we're interested in a specific place on the Earth, and we're interested in a certain time period, and we want low cloud cover, is essentially what we asked it for. And it's returned back this list of data that we can get. We have not downloaded the data yet. We've only looked at the metadata. So our next job is to decide how we want to, what data we want to download, and then go ahead and download it. So for our analysis, this is all in preparation for running. We're gonna do some basic exploratory analysis with the data we download. We're gonna look at some of the like the shape of the data, and then we're also going to run a couple of normalized difference indexes on the data itself, just to give you an idea of what you can do, because we haven't really looked at any of this yet. It's all been like code and text. So we will get to the pictures in a minute. So the next thing that we need to do is pare down that giant list of assets. So we don't want to download 20 things for this. We actually, for the analysis we're doing, we only actually need 3 bands. We need green, we need red, and we need near infrared for the 2 different indexes that we're going to run. So this line of code basically says, we're going to select the assets that we want. So we're passing it the results, the list of results that we had. And we're saying these are the asset the assets that we want to have. So we're only getting band 3, band 4, and band 8A. So I'm going to run that. And it's going to make a list of items for us that we can work with in a second. Okay. So the next thing we are going to do is get the URLs. So basically the web address where each of these items lives so that we can download those. So I'm going to run that code. And the reason that we want to do that is because this is how we're actually going to access the data. We need to know the exact place on the server where this lives. And so we're going to ask for them specifically by URL because URL is essentially, it's like an address, right? It tells the computer how to walk down the file structure and find the thing that we want. So this list of URLs is going to be really important. You can also, you can actually get some information from the URLs itself because of the way that these are structured for this particular catalog. So really importantly, there's a little bit of date information in here, and then also what band each of these items is, or I guess assets. That scrolling traditionally is causing problems. 2-finger scroll, that helps. Okay, so we're going to decide which ones we want to download. In this case, we're going to work with the first item in the list. It actually is a really nice image for what we're trying to do. So the URLs that we're going to get here are from item number 1 on the list. I'm going to run that. So remember, for each of our items, we have 3 assets, which is the 3 bands that we want. So we're going to get 3 things here. So now we're going to actually start working with the data. So we've actually downloaded this. Our green band is the one we're going to work with first. So if you're familiar with the raster package, this is not new. But one thing that might be new if you are familiar with the raster package, or sorry, with Terra. They are synonymous in my head, but they have changed places. One of the things, one of the parameters you'll want to be aware of is this VSI equals true. That's going to tell Terra that we're working with a URL instead of a file path on our computer. So it's going to tell it, hey, go look on the internet instead of look on my local computer. So we are going to turn that first asset there into our green band. So now we've saved that particular piece of data as band_green. Yeah, question?
That said it couldn't use the argument VSI equals true.
Oh. Good question.
How recent is your Terra version?
I need to update it. I'll check.
So for the folks online, the question was that the VSI equals true parameter in that line threw an error, and Alex suggests that maybe Terra needs to be updated in that case. I see is there a new chat thing?
So Charlie's asking if this collection is cloud optimized. Charlie, this collection actually is cloud optimized.
So I don't know if you can hear, but yes, this collection is cloud optimized. It's a fun game to play telephone in the room. Yeah. Yeah. So now we've loaded, most of us have gotten data to load into our green band. So we have green loaded in. Yeah, sure. Here,
So because this is, Terra works a little differently. Terra doesn't actually load data until you need it. And so what we're doing here with the first one is we're telling Terra where the green band is. The only thing it's reading is a little bit of metadata from the file. It actually hasn't read the file yet. And so that's kind of a big difference and has to do with the whole cloud optimization thing. So it'll make a little more sense in a second.
Okay, so the next thing that we need to do is there's a little bit of, I guess, jumping through hoops to get the extent the way that we want it. So that's what this line about working with the projection here for the green band. If I'm correct, I know you wrote this line of code, but the point is that we are making the coordinate reference system work with the data that we have, so everything matches up the way that it's expecting it to be. So we're going to reproject our scene into the right coordinate reference system. And then, sorry, oh, the bounding, you're right, it says extent. So we're making the extent be the correct coordinate reference system. And then we are going to apply that to our green band that we just set up so that that is also in the right coordinate reference system. We're gonna run that. So this is all the typical projection hoops you have to jump through to make sure everything matches, because as you all are probably aware, if your projections don't match, you are working in two different universes and things don't line up. So with that, now that we have that UTM extent item set up, we can use that in our bands for our red and our infrared when we load those. Yeah, Naomi. Oh, ask anyone.
Yeah, because EPS is WGS. 4326 is WGS 84. So I was
Good question. So the question for the folks online is, it's telling us that the coordinate reference system is EPSG code 4326, which is lat long WGS 84. Why is it called UTM extent? That's a good question, person who wrote the code. I'm looking at Alex.
Yeah, so in this project code, what we're doing is we're taking the extent object, we're telling it that it's coming from 4326 and it's going to whatever the projection of the green band is. So we're actually reading the projection out of the green band metadata. No. That's the whole point of HLS data is in UTM, and the zone is going to depend on where the scene is. And so rather than us having to know what projection every scene is in, we just ask the computer to read it from the file or from the STAC metadata and tell us what projection it actually is.
That's on WGS 84. When we talked to HLS, that's an ETM. And we just said, hey, go read whatever it was from the thing we got and make it so.
Yeah. So for the folks online who couldn't hear that, I think the important point to make here is that the catalog and our queries are working in one coordinate reference system. The data that we download can be in a different coordinate reference system. In this case, our catalog wants everything in WGS 84 for the queries, but the data we're downloading is actually in a UTM coordinate reference system. Good. All right. And we can find out too, like you can always look at the help for this project command to get information about like what each of these parameters is. For me, since Alex wrote this recently, I can ask him what it was, but if I was reading this on my own, I would just go ahead and query the help for that command, and then it would tell me what the inputs are, and then I could figure out what that is. But so hopefully that makes a little sense. It's always good to ask questions about the code because you have the people in front of you who wrote it, which is a lot easier than trying to figure it out later. Okay, so we did make sure I'm writing everything. Okay, so we just ran, yeah. Mm-hmm. Okay, so the question for the online folks is, do we prefer project over transform? Is this just a Terra thing? Like the way?
Is there also a transform command in Arrow?
I don't know.
I think part of it is because we're working with an extent object, not a polygon.
It's telling me Terra doesn't have a transform.
Yeah, I think transform might be the SF terminology.
Yeah, that's a good question though, because sometimes different packages or different tools will make a distinction between like project, reproject, transform, those kinds of things. So it's important to ask those questions. But I think in this case, the project command does what you're thinking of as a transform. Yeah, language is really sometimes tricky in the case of projections, more often than not. Okay, so we loaded our green band. We made sure that the computer's aware of the coordinate reference system that it's in. Now the code gets a little bit less complex when we load in our red and our infrared bands. or we can think of those as assets in terms of STAC catalog. So we can include this parameter for our UTM extent that will do the projection stuff that we needed to do. Okay, so now we have our 3 bands. We've got green, we've got red, and we've got infrared. Those are the 3 bands that we need to do our index calculations that we want to. So the NDVI, normalized difference vegetation index, and NDWI for water index. So with that, all of these normalized difference indexes have the same format. They have one band minus another band divided by the same band plus the other band. So it's always minus on top, plus on the bottom. And it just matters which band you put into that calculation, whether you get, for example, vegetation versus water. So with vegetation, we're going to work with red and infrared, and with the water one, we're looking at green and infrared. So, but the math is the same, so we can write a function so we don't have to keep doing the same coding over and over again. You could just write this out in code and it would be fine, but if seeing it as a function is helpful, I think that's kind of a nice way to make your code a little cleaner. So we're just making this function. We're saying, hey, R, make a function, give it the inputs X and Y. And then what are we going to do with those X and Y inputs? Well, we're going to take X minus Y, and then we're going to divide it by X plus Y. So that's what the math is going to be. So we can set that up in that function. And now here's where it makes the code nice and simple. To calculate NDWI, so normalized difference water index, we can use our norm diff function, and we can just say, hey, function, why don't you give me the index with green and IR? And so it's going to plug that into our formula up here and going to give us the output. Same thing with NDVI, so normalized difference vegetation index, but we're going to give it the infrared band and the red band and let it do the math for us. So it's basically taking these 2 images and it's referencing, you know, pixel 1 on this image, pixel 1 on that image, do the math. Next pixel, so pixel 2, and it's doing the math like each of the pixels that line up with each other. Okay, so we're going to run that. And again, no fancy output yet. We'll take a look at some visuals in the next couple steps. Okay, so those ran. So what I have under the hood, which you can't see at this moment, is I've got 2 raster images. One has our water index, one has our vegetation index. I promise I will show them to you soon. So one of the things I ended up doing when I started working with this data was like, okay, I finally got this index. We went through all of these hoops to, you know, get the data, filter the data, finally pull it down. And then I looked at it, was like, what on earth is going on here? The ranges on this data are really funky. So like if we look at the histogram, so we just run hist on our normalized difference water index NDWI item, and we say, give us 40 breaks because something weird's going on. Because this is a normalized function, we expect the range to be from -1 to 1. It's normalized, so it's like 100% minus, you know, and then 100% plus. But that's not the case, because if you look at the histogram, it's making bins from -40 to 80. Like, uh-oh, what is going on? What happened here? Okay, so green is a little funky. And this is normal when you get this kind of data. You start looking at it and you're like, what is going on here? Something is weird. So we're going to do this exploratory analysis. So we go ahead and look at the summary of the numbers inside of our raster. You can do this because a raster is essentially just numbers that get arranged in a specific way. So I can just look at the numbers and I'm like, oh yeah, my minimum, -41. That's like 40 more in the negative direction than it should be. Okay. Then what's going on? We also have max of more than 85. Also not what I was expecting. Okay, so we know that that's going on. Let's look at the green band. Similar story where our green band, if you look at the histogram, is very tailed. So it has very high values. Well, not very high, but definitely higher values than we maybe expect. Actually, no, this one's looking okay. So we're going from about 0 to 0.6. So maybe that one's all right, but a little concerning. If we look at our NDVI, same deal. We've got some funky stuff going on, which we might predict because the water index one is also a little funky. Okay, and we'll look at the summary too for that. So what's going on here? My interpretation of what is happening here is when you have satellite imagery or any kind of like return over water and you have sun glint, you have a lot of light coming down and bouncing back, sometimes in a concentrated fashion. So if you think about like choppy waves, you have all kinds of shapes, right? And so when you have a situation where you have like concave shapes, it's going to funnel that, like if you've ever taken a magnifying glass and put it in the sun, how you can concentrate the sun's rays, that can happen with choppy water. So my guess is some of these really high and really negative returns are just because of the water that is in these images. And you haven't seen the images yet, but trust me, it's like diagonal line. Half of it is land, half is water. And so I think that's what's going on here. So in order to do the plots and have this actually look like what we expect it to, what we're going to do is we're just going to filter out those really negative and really, really highly positive values, because when you see the results, I think you'll agree with me that that actually fixes the problem. So if we were to just plot it and not filter, essentially it'd be really hard to see what's going on in the areas where we want to see. So like over land, everything just kind of washes out because our values are so extreme. So when we apply the color ramp, everything in the middle is just kind of gray, essentially. So what we can do is when we plot, we can make sure that we apply a range filter to only plot the values in the area that we want to see. So when we make our plot here, the first thing I'm going to do is I'm going to set a layout, and this layout, I recommend looking at the QuickR website. They've got really good examples of how to work with the layouts in R. But essentially what this does is it makes one big plot in the middle and then two little plots underneath. So that's what all those numbers basically reference, how many slots are available and what the columns are and things like that. So check that out. And that's where I figured out how to do this, is with the QuickR website. So use that as a reference. So this line basically sets up our layout and says what slots R has to put an image and how big to make them. Below that, we're going to plot our three images. So we're going to plot our NDWI, and we're going to plot our green and our IR band, so we can see all three of those. So the two inputs on the bottom and then the output on the top. And this range filter right here, I'm using that parameter to tell R to only plot the values that fall between -1 and 1. If they're outside that range, don't plot them. And I'm going to use the blue color palette, which you can kind of see is down here already because it remembered that I ran this before. So I'm going to run that line of code. So it's going to run my 3 plots and it's going to output them on the screen. I think it's kind of nice to see the inputs for this. So you look at, now you can see all this water and look how choppy it is. That's why I think those really weird values are just from the water returns. And actually, if you filter them and only look at the like really negative and really positive values, you'll see they're all in the water anyway. So you can kind of play with that. Okay, but what can we learn from NDWI? I feel like we're always talking about like vegetation indexes and not so much about water. If you notice on our water index return here, this sort of medium blue is the extent of the dune system. So cool. I mean, I think this is cool because I think about dunes a lot and things like that, but sandy dunes actually have a really high capacity for holding water, which you might not think because it's like sand. Doesn't water just go straight through it? But it doesn't in this case. So we can actually, if we can figure out what these ranges, like value ranges are for the sort of medium blue here, we can pull those out and we can actually extract what the extent of the dune field is just using this pretty simple index. So I think that's super cool. This is the kind of stuff that just makes me like, oh my God, this is so cool. It's just a picture. It's a whole satellite system, but you get the drift, right? Like for me, I'm downloading a picture and I can be like, here is a dune system right here. So that stands out actually really nicely. And we can take a look at the inputs, the green down here and the IR here. I think maybe the IR is a little bit easier to understand. That sort of the sand is reflecting in sort of that medium area for infrared. This green color palette maybe isn't the best one to use, but it was a green band, so I couldn't help but make it green. So that's one. I will say, plotting this in regular R, not in Quarto, this graph actually looks better. It's a little bit better proportion. So I didn't have the time to figure out how to make the graphs look better for Quarto. But also we can do the same, basically the same set of code with our NDVI, so our vegetation index as well. So the inputs on that are red and infrared bands, and we're doing the same math that we did with the other one. And so you can see this one might be a little bit more intuitive to interpret, because I feel like we, especially in intro, like remote sensing classes, we spend a lot of time talking about NDVI. So the idea is that the darker colors are healthier vegetation in this case. You'll notice what's going on in the water. There is not really healthy vegetation in the water. You need a completely different index for seaweed that's submerged. So this isn't plants over here, random plants. It's just, you know, weird scatter stuff. But if we look at the land, you can kind of get an idea that there isn't really a lot of vegetation per se in this dune field area that's being picked up by this index. It looks pretty blank. But what I will point out is, if you've ever seen dune vegetation, it is like the epitome of California plants. They are small, they are shrubby, and they are coated in silver hairs. So they often aren't picked up very well in satellite imagery, just because they aren't really green. They're very light colored. They're in a really intense sunlit environment with no overstory. There's generally only one layer to the canopy, and it's only this tall usually. So they are armored for typical California beating sunshine in the summertime. So they don't really show up very well in NDVI calculations. But you can see the sand pretty well in this case, I think, and maybe get a little bit more nuance to it than you saw in the water index. So sometimes combining these can help us with our analysis in different places. So I think that is pretty much what we've got for today in terms of code. So we've got a little bit of time, maybe 10 or so minutes before we should, turn the room over to whoever has it next. But we've got a little time for questions from the room, but also from our online folks. Yeah.
Maybe this other methodology to expect it, and I have in mind that you have a shape file probably of the extent, and now you want to compare it. How would you combine the packages with Terra, and then you want to crop the shape and compare?
Yeah, I mean, you certainly can crop these images if you had like a shapefile that outlined the extent. What I would probably do if I wanted to compare them would be if I could figure out sort of what the cutoff is for, like, say I was using the water index. So if I scroll up a little bit, I can wave my hands at this image instead. So like maybe if I knew that these sort of like whatever value these sort of mid blues are, I could extract all of those pixels and turn that into a shapefile with, filtering for like getting rid of the little teeny tiny ones, polygons that we would get. And then you could difference those two. So you could have like the one maybe you digitized by hand, and then compare the one that you extract from the imagery, and then difference them maybe area, or even like do like a difference function on them to see like what areas we're not picking up as humans, or maybe things that the index is missing or adding, or things like that. So if just off the top of my head, if that was my question, I'd probably go with vectors. So, so I mean, yeah, so for the folks online, the question is like, how do you combine like polygon information with raster data? I think really the key is you need to pick one. So you could take your shapefile and turn that into a raster. Like maybe I have my same extent that I have here for raster, and I can put my polygon on there, and there are functions that can turn that into a raster. So you could have like a yes and no raster. Like, this is the thing I'm interested in this area, but over here it's not. And then I could do a difference with my my satellite imagery especially if I had done some extracting, like some classifying of the pixels and compared that way. So I would either turn them all into vectors or turn them all into rasters. And then you can do, essentially you can do math with it at that point, but it's really hard to compare them separately. Like if one is a polygon and one is a raster, they kind of aren't talking the same language. So I would definitely encourage you to maybe try thinking about like, which one can I convert to the other format? And then how would I work with it from there? Yeah. Yeah, good question. I see our chat has more things that I haven't seen.
Oh, I just realized that Charlie's question needed a little more
Okay,
clarification.
do you want to talk on
Yeah.
Mike for answering that one?
So the one thing I wanted to point out is everybody noticed how fast this went, right? And the reason why it went fast is we only downloaded a very small part of the Landsat scene. We should actually probably put a diagram in here of like how small a portion of the file we used was. And we didn't download the whole file. We only downloaded the little bit that was in our extent for each of the bands.
And that's where the cloud optimized part comes in and makes it possible. If this wasn't cloud optimized, we wouldn't be able to extract it this way. We'd have to download the whole thing and then crop it and then work with the cropped image. But because it's
The
cloud
code,
optimized, we
yeah, so this was the interesting part is this code will actually work if it's not cloud optimized. It will just be much, much slower. Like it might not be done yet. Slower.
because we're downloading 3 Landsat scenes.
Right.
So, which are quite large.
So like the code we wrote actually works whether or not it's cloud optimized. The fact that it was cloud optimized let this code run much faster.
I think this also brings up the point that you can do this kind of analysis in a more traditional way where you go to like, one of the USGS online sites where you plug in the interface, all the things you're interested in, look at the results, download your scenes, put them on your computer, especially if you only need 3 layers, like not a big deal, right? So you can download all that data, I can work with it locally. But we have to store that whole scene typically when we do that. But then also if we wanted to like, I don't want just one, right? Like I want a time series. I want all the data. So I don't actually have to store this data. Like this is all in my temporary files right now. I can let NASA keep my data and I can just have code that pulls down information and does my analysis. And when I'm done, I can get rid of all of that stuff I've downloaded, but also I don't have to download huge chunks of data. I can only grab the data that I care about. And then, as I decide I'm going to do this 100 times, I don't have to store all that data. NASA can keep it because we're working with this STAC catalog and the data is stored somewhere else. Yeah, question?
Save your results.
Yeah.
So you did all these calculations and you produced your answers,
Mhm.
you could save your answers.
Yeah.
So that if you wanted to do another future analysis on your answers, like overlay a polygon and do some other calculations, you could pick up from there and not have to do the
Yeah.
downloading step again.
Yeah, I mean, obviously, like if I wanted to include this as like a figure in my journal article, obviously I'd output that. But the point is you don't need to save all those intermediate products. You might potentially want to save like the first thing that you download, but I wouldn't save any intermediate things. I might save, if I was going to save anything, I'd save the first things I download and the last things that I output and let the code handle the rest. Like if I needed to reproduce that, I would just let the code do it.
Let's say what you've done today and tomorrow you want to go on there, so
Mhm.
you download it again.
Yeah, so for the folks online, the question is if I have this code and maybe tomorrow I want to add to it, would I just rerun it and download the data again? Potentially, yes. I think there's ways to cache it in R where you could come back to it. What do you think?
Well, that's the part where I'm saying if the next step is to just work from the calculated NDWI and NDVI, I might save those as local files.
Yeah. And then have a separate code file that works with it from there. So you're not having to constantly re-download the data.
Okay.
I mean, there is like, as you're developing stuff, there is a little bit of like re-downloading, but the nice thing about, and in particular with this analysis, it's such a small geographic area, it's not a big deal, but yeah, if it was something really large, you might want to download it and have it local. Yeah. So there's, obviously it's sort of work with it the way that works best for your particular question and situation, but you have the option to not keep anything locally if you don't want. And the nice thing too is you can give this to a colleague, and because everything lives online, you'd be like, here's my code, just run it. And because it can connect to the internet and grab the data, you don't have to give them the code plus all the files and make sure they've got it in the right folder in the right space and your file paths are right and blah, blah, blah. Like, it's just, here's code. The internet will take care of you. This, of course, assumes the internet keeps working and the government can keep funding the data sets. Vote accordingly. I will say there are some choices that can help ensure that this continues to be an option. So yeah, it really is a matter of like, here's the menu of options that you can use, pick what works for you. And I'm not saying that you should never download anything. I'm just saying you have the option to potentially not. Yeah. So question to that.
Little thing at the end, and then download these pieces of content that you can just run in front of them on a farm. That's sort of the idea.
Sorry, ask that again.
There's no line of code in here currently that downloads anything to your computer. So if you wanted to do that, that'd be something you'd add on to that.
Yeah. So for the folks online, the question was, right now, this particular code doesn't really save anything out explicitly to a file on our hard drive. And that is true because this is a workshop file. We didn't save it out, but potentially like for research, you would save out your NDVI file, your NDWI. That one's much harder to say. You would save those out because they're the end product. They're what you care about in this particular analysis. So yeah, you can save out those files to an actual file on your hard drive, like save them as a GeoTIFF, for example, to use later. But we didn't do that in this case just because it's a workshop and I don't really want to clutter up your hard drives with stuff you'll find 2 years from now and be like, what the heck is this? But you can save these. You could save any of like the intermediate stuff that we did as its own file if you needed it. And honestly, like this is sort of exploratory. It was like, well, we're going to replicate this analysis that this person presented about at this conference. And there's sort of the exploratory analysis that happened when I plotted it and was like, what the heck? Why is this looking this way? But I mean, that's a really normal process to go through. So that's sort of what we're trying to illustrate today. But you could definitely take this further and you can definitely save out files as needed. Yeah. Cool. Well, any questions from the folks online that we should? Okay. Okay. I think this will be the last one and then we should clean up and let the next folks in.
Sure. So a question came up about like where to look for data, especially if you want to find data that is STAC cataloged. And so the group behind the STAC specification has this website you can go to.
And I think this is linked in our
it
workshop
is
somewhere. Where exactly, I don't know, but I'm pretty sure it's there.
And so this page lists various STAC catalogs that are available that are public. And so you can look through here. So like if you wanted, this is Brazilian satellite data. And there's some different collections of, various combined data sets. You'll find the NASA one on here. You'll find the planetary computer on here. You'll find the USGS one on here. This is the place to go and find the best examples of STAC catalogs that have a lot of the data that you're looking for already.
I will say, have patience with these. If you find a catalog that you think has the data you want, one of the challenges that I had is somebody who's understood the concepts, but was new to actually working with these, was that some of them aren't as well documented as I would like. So reach out on channels, like mailing lists on, if there's a GitHub repo for the catalog or things like that, reach out to the folks who make these and ask them questions because it will help them know how to work with the public and the consumers better. So if you have questions, don't hesitate to ask, but also feel free to, like DataLab has now 2 sets of drop-in hours. Feel free to come chat with me in office hours for DataLab. And even if I don't know the answer, I'm happy to sit down with you and we'll figure it out together. So you're not stuck if you open up one of these and you're like, wow, I really don't know how to go on from here, even though I think this is the thing I need, but it's opaque for some reason, reach out to folks who can help. That's what I did. I was like, oh, I'm going to do this. Should be easy. That was the first thing I thought. I was like, I know how to do this. Like this person showed me how in this presentation. So all I need is my data. I can calculate the indexes, easy peasy, right? Like 3 months later, we have a workshop to show you how to do this because I found it difficult. So come talk to me, ask questions, ask for help. So I will leave it there. Thank you to the folks online who are here. We're jamming to cell phones in this room, which I know you guys can't hear online, but thank you all for coming. And I will end it here, but hopefully we'll see some of you in person at some point as well. So bye all online. Oops. Stop the recording.